Hello, my name is Jane Crowley, and this is my Lab 3 Magnetic Field of Permanent Dipole Magnets lab video report. In this lab, we measured the distance dependence of the magnetic field due to a little bar magnet, and we compared our measurements to the distance dependence predicted by the equations for on and off axis magnetic fields that are derived from the Biot-Savart law. And so here you can see the equation for a magnetic field of a dipole on axis. And so just some background information on magnets and magnetic fields. So magnetic field lines point into the south end and out from the north end. Magnetic dipole moment points from south to north, and then superposition similar to electric fields. B net is calculated as the sum of all the vectors present in the B fields. And some other equations that I will end up using later in this lab report are these two right here. And this just describes a general form for magnetic fields. And then this one here is specifically for the X component. So for this particular lab, this is just a setup of what the experiment looked like. So we had our phone, and we used an app to like get data for how the distance and measuring the magnetic field. So this gray rectangle here is the magnet. So you can just see what the general setup of the lab was. And so this is my data and my chart for the graph. And you can see here what the BNet in Tesla was predicted to be, about 4.9 times e to the negative 5. And then from there, so for my calculations, I used one of them from the equations page, the one with the natural logs in it, to get that n was negative 3.1438, and that's from the slope of the graph, and it's supposed to be around 3, so that's pretty accurate. And then ln of k equals negative 14.7, which is my y-intercept, so I got k is 3.9 times e to the negative 7. And then from there, I was able to calculate u to be around 2. And then into my computational model. So this was my equation for the dipole B. And so I just put in the code there. And then here I scaled the arrows, and this was the value I chose. And then here I changed the distance to be one of my values. And this is how I changed all the vectors for that. And then this is my code for creating all the arrows. So you can see how I calculated like each R axis and then did the arrows with the dipole equation that I created earlier. And then I used rpert for 1, 2, 3, and 4, and also used the dipole equation there. And so from there, I had another 45-degree angle one that you could see there. So this is what my model looked like once it had run. So you can see the 4 arrows or the cyan ones, and then the green one, and then the purple one back there is the 45-degree angle, and the white cylinder in the middle is the magnet. And so here you can tell that the B at 45 degrees is you can see in the output here. And so this was the predicted for my calculated value. And you can see that they would be in the same order of magnitude. So that was pretty good, even though they're a little bit off. So there was some error. And so which of these statements describe what you observed? So when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. I noticed that. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And then for these what if questions, we hadn't oriented the experiment to compensate for the magnetic north and instead laid out the meter stick at some intermittent angle with respect to Earth's magnetic field. The change would have resulted in the exponent being non-zero. And then if we stuck two identical magnets together end to end, I think that the magnetic field would be greater by a factor of about 2 because of superposition. So that's the end of my presentation. Thank you for watching. Hope that covers everything. Bye.